and some of our methodology and kind of the motivation for us to decide it with the idea that maybe some of these needs are also reflected in other parts of the other scientific domains, and using AMPEL for other scientific purposes would just be a lot of fun. So I will mainly talk about some use cases, and if any of them resonate, then please contact me afterwards. That's my main message. So I'm, as mentioned, working for the Punch for NFDI consortium. So we're doing basic research into fundamental physics. So it's a collection of particle physicists, astrophysicists, and astronomers. So representing quite a wide range of different communities. But let me directly switch then to a number of different use cases where I think that AMPEL could be useful. So briefly summarized, AMPEL is a platform or set of tools that allows for the systematic execution of different analysis units while trying to take care of all the boring stuff. So where could that be useful? One immediate area could be the analysis of real-time data streams. So this is becoming more and more common now. We have many different sensors that pick up measurement values in real time. And these data streams are so large that you can store them into database and hope to efficiently query them for some subset of data. Rather, you have to analyze the data as it's coming along and analyze it and react to it when you need to. Another area that's already standard in industry, but becoming more and more typical in science, is that you have to work with long-time modular software development. So I don't know if you can see my arrow, but the little schema to the right is supposed to reflect a complex analytic workflow. And this is by now much too complex to be done by a graduate student during a short work period, but rather it's work that needs to be carried out across different institutions, so different locations, and across many generations of scientists. So we need to have methods and platforms where we can jointly collaborate on software and make sure that this can be maintained over time. Continuing, we might have to deal with heterogeneous data sources. So we have different ways of grabbing data into our system, but it might not be enough. We might not know how to actually interpret this data. This might vary between different users and different domains. So it can be the different things in, for example, these images might be interested, how many legs. It could be that completely different aspects are actually of interest, maybe sounds. So use cases might be that you need some sort of translation layers between input data streams and what an individual scientist actually are used to working with. This image here is taken from some discussion of autonomous driving. And this is an example of an area where provenance is getting critical. So we have many different data streams and you take action on them in real time. And you do need to make sure that you can recreate what was known at a specific point in time and what action was taken and what was the consequence of that action. So as I mentioned, this is an example of autonomous driving, but similar situations appear in a lot of different places. Another kind of invented scenario, but what I still think is pretty common, is when you are doing repeated analysis of large data sets. So repeated analysis, but maybe with slight variations. So you might change some analysis unit, you might have updated some of the data, and you want to rerun some sort of analysis pipeline. And when you have large data set, this becomes very resource intensive and wasteful. So if you can have methods for deduplication that make sure that if a calculation has been done at some point, it is not repeated, then this is certainly advantageous. And a final aspect that might encompass a few of these different aspects is enabling code to data in science. So this is, of course, also pretty common in industry, where you have data sizes that are much too large for an individual scientist to work with. So you need to have some aspect where you're locally in test environments designing your workflow, and then you can somehow push that into remote site where the actual calculations are being done, and then you're fed the result. So these are all use cases that is in one way or another related to AMPEL. I'll return to them again. But if these things are what's important to you as well, then you might have something to gain from looking into using AMPEL. Now I'll take a step back and return to the field of astrophysics, so where I'm coming from. So what is that actually, and what is that we're doing? So I've here listed kind of the three, or my main three, large-scale scientific goals. So first of all, we want to figure out where is the universe coming from and where is it going. So now we see that the expansion of the universe is accelerating due to something called dark energy, but we know very little of what it is. This obviously, by measuring this expansion even finer, we can hopefully learn more about what is going to happen to the universe. Another area has to do with studying energy regimes that we cannot reach at labs in Earth. So the bottom right figure shows the energies of particles hitting the Earth continuously. And the green arrow shows kind of roughly the energy levels that we can hope to create at the largest, most energy-rich labs on Earth. And as you can see, the particles that that come from space can reach many orders of magnitudes higher energies. We still don't know quite where these are coming from. We don't know how they can be accelerated to these energies, but if we can find that out and also study these processes, we might be able to study what happens at physics scales that, again, we can't quite study in our own labs. And the third aspect has to do with Einstein's theory of general relativity. So this describes gravity on scales of the solar system very, very well. But we also expect that at some point it needs to be tweaked, updated, extended, and quantified, but we don't know quite when. The bottom left figure shows a simulation of what we expect the universe to actually look if we could just see gravity, but we can't. So instead, we have to use other metrics to try to recreate this web of density and see whether it matches with these simulations. So these are kind of all the large-scale goals. How do we hope to get there? One very powerful way is to work with astronomical transients. So this is what we're looking at here. And at first glance, it does not look very spectacular. So we have something pretty standard measurement sequence. So we have time on the x-axis and brightness on the y-axis. So we see something that starts off and it goes brighter, and on a time scale of hours or days or weeks, it reaches a peak and then it fades away. At the same time, we have points of different color. These are coming from different detectors. In our case, that's from different telescopes with different sensors. Now we have some vertical error bars that illustrate that other things happened. So in general, this time sequence does not look in itself that exciting. But if you look at it closer, it turns out that it really is. So what we're looking at is a tidal disruption event. So this is what happens when a star gets too close to a black hole. Some of it is being eaten by the black hole. Some of it is being heated so that it can emit exactly the light curve that we're seeing here in the middle. And by this observation, we can actually test a lot of these fundamental theories. Obviously, being close to a black hole is a region of very high gravity, so where we really expect to test general relativity. We can test a region of structure formation around a black hole, so in the core of a galaxy. One of these vertical lines illustrated that a neutrino or a ghost particle for some reason was emitted. We don't know why, but we could detect it here. And then finally, by observing many such transients and enabling and measuring how far away they are and how old they are, we can hope to trace out the universe. So somehow map how it's evolving and thus constrain dark matter and dark energy. So these are all the things we want to do based on these sorts of events. And it's exciting, but it's of course not easy. And why it's not easy is since we're dealing with a prototypical needle in a haystack kind of problem. So these events are exceedingly rare. We have to search among billions of galaxies every night to find these kind of single golden nuggets. So to do that, we design very large cameras. Little middle figure there shows. So it's very similar to what we have in our cell phones, except much, much larger. And then we put these sensors in telescopes, and we put the telescopes on the top of mountains. And with those, we can then start to observe the nighttime sky. And we try to cover as much of it as possible. And this is working pretty well, and hence we've been able to discover, for example, TDEs the last year. The downside is, of course, that we also detect millions of real but boring astronomical variables. So the histogram at the bottom kind of illustrates that every few years we get an order of magnitude more detections of real events every night. So the real trick becomes sorting through these and finding out which ones are actually the really interesting events. And this is made even harder by looking at non-optical messengers, so non-light. And now we have observatories both looking for gravitational waves and neutrinos, so these ghost particles. So you might have heard of LIGO Virgo. That was a Nobel Prize a few years ago. Basically, they can sense a slight squeezing of the Earth due to a passing gravitational wave. This is and then we have in the middle, we have the IceCube Neutrino Observatory. So this is a cube kilometer of ice where we can hopefully see neutrinos passing through. So these are completely different kinds of messenger, but they also provide some information about what's happening at some location in space. And by combining that data with optical data, we can hope to trace down even more exotic particles. And then briefly returning to the Punch for NFDI program, this development with detectors is increasing all the time through technological developments. So pretty soon we will have radio telescopes that produce hundreds of terabytes of data per second. And the LHC collider will be upgraded at CERN and produce even more high energy protons that hit each other. With the consequence that you would need even larger farms of computers to just process this flood of real-time data. And then in the future, we'll be in the position where most of the data we won't be able to store. We have to process them in real time and throw away most of it. And then a lot of the Punch for NFDI work goes into understanding how do we actually do that in a systematic way so we can still recreate what happened. I won't go into detail about that, but here is a link there. So returning to the problem that we had before, we kind of had initially the promise that we have all of these sensitive real-time detectors with which we can use the lab as use the universe as a lab to test fundamental physical laws. The problem that comes with it is that we have high throughput data streams. So multiple data streams that, of course, can be combined in different ways that are much too large for an individual scientist to use. And added to this problem, we have many different scientists that want to use the same data for different science goals. And the final aspect is that we want to allow scientific exploration. So the figure to the right kind of illustrates how astronomers worked a century ago. They were standing with their eyes looking up into the universe that was kind of foreign and violent, and they were talking and trying to figure out what happened. And a lot of astronomers still see themselves that way. It's a field that's kind of filled with small groups, each looking into their individual theory. And we kind of want to keep this scientific exploration or creativity, even as in the current era of large data sets. So that would be great to be able to keep. And then finally, we want all of this to be fair. And this is not only for proposals in astronomy and astrophysics. That has an additional aspect in that we don't control the universe. We never know when an event will repeat itself. So we'd better make sure that we record what happens and that we can recreate what we did. And this all then has led to the development of AMPEL. And finally, I can start to describe what that is. And you can look at it from a few different ways. You can say that it's a methodology for deconstructing workflows. You can say that it's a workflow manager for executing arbitrary analysis units, or you can see it as a real-time system that runs all the time and produces scientific results. So I will talk about all three of these aspects, but I'll focus on the first one. And kind of the guiding principle has been to create a system where everyone can do what they are good at. So scientists can develop their analysis algorithms, instrument specialists can devise metrics for how to actually use the data that they're getting, and software designers create systems that are scalable and maintainable. And then throughout all of this, we want provenance and reproducibility to be built in from the start, meaning that this is not an afterthought that relies on an individual scientist fulfilling a set of requirements, but rather something that you really can't avoid to do. So we'll start by talking about it from a methodology point of view and returning to this TDE light curve that we saw before. So then this is the typical kind of object that the TDE scientists are interested in. So it has a particular light curve shape. And then we're dealing with other science groups that are interested in different kinds of transients that have subtly different shapes. And when we set out designing AMPEL, it was the question, so how can we deconstruct the kind of science operations that they want to do into a set of abstract rules that with which we can apply, we can interpret all of their science goals. And we concluded that that can be done by 4 distinct types of operations. So add, combine, augment, and react to data. And these are kind of all things that we can explain to the scientists what they mean. And in terms of this example, adding data means either by filtering a real-time stream or grabbing data, you then obtain data from some sort of system and you add it to your light curve from some source. Can combine data, so aggregate the knowledge available at some specific point in time. And this could be simply to integrate all data up until a specific point, or it could be a more complex query where you're really trying to figure out which data points from a set of sensors could have some sort of causal joint origin. Third step, you then use the data to derive new knowledge. So this could, for example, be the TDE probability. And then in the fourth kind of operation, you summarize what you know at a certain point of time, and then you trigger reactions if you want to. So this could be anything from a real-time alert that some astronomer should wake up, or just a generation of a pretty figure. So the first step was to think basically that these are 4 types of operations with which we can describe what most people want to do with this astronomical data. And what's nice is that these 4 kinds of operations can also be described in a completely general way as 4 separate execution layers. So in the first execution layer, you decide what data point to add to the system. In the second execution layer, you decide how to combine these data points into states. In the third execution layer, you can then take the information available in state and add more information to the system. And in the fourth tier, you then look at the information available, and for example, if some threshold is exceeded, you then trigger a reaction. So this was kind of the starting point for the AMPEL development, that we describe workflows in terms of these types of operation. And they are all really unique in that they have specific requirements for the type of input and output data they expect. And these are things we can then specify by a set of abstract classes. So this little Python thing is, of course, not something to read right now, but it's an abstract method that, in this case, in the T2 tier, specifies, so what kind of data structure should you expect? And with this setup, we then have a system where the same set of data structure can be interpreted by a scientist from a domain point of view. So for scientists, this T2 operation might be pretty straightforward. To assuming the data are coming from this sort of light curve, we can evaluate or compare with a model and say, is this likely to be a TDE? And the same set of tasks, the same code, from a system engineer point of view, this is seen in a completely general setup as a task to be scheduled and executed, and the needed data imported, task run, and the data exported. And then we will finally get to a stage where we can design a full scientific workflow based on this tier definition to the left. So what the domain scientists will do is that they will basically encode the individual steps of the workflow as individual units, and based on their functionality, they're then defined in one of the 4 execution layers. So in this sense, they build a domain-specific library of tasks, and then a user can design a full analysis schema by picking from each of these layers, so which are the units that I want to use with their configuration, and then put this together in an analysis schema, which in principle is a YAML file that then lists, so which are the steps that should be done, and taken together, they then form a unique analysis. So this kind of ends this methodology setup. We deconstruct workflows according to these 4 tiers. The scientists implement their domain knowledge into these methods and then construct the full workflow through specifying which units to carry out. After this, we can then move to the next step, which is really how to execute these workflows. And there are a few different ways that can be done. In principle, this is carried out by the AMPEL core set of methods. So these are completely application agnostic methods that can take these workflows and execute them. Basically figuring out, grabbing this correct software that should be run, finding the relevant data that belongs to the challenge, running the unit, and then storing the output that you get from the execution. And since we have 4 different tiers, they are completely independent and can be scheduled and parallelized at will. And there are actually 2 ways to execute these workflows. Either you do it serially or locally. So any user can install their own AMPEL installation that they then use as a sort of development or test setup, where they finalize their workflow. And once that's done, they can upload the workflow to a high-performance computer center where it's being run in a parallel mode. So this is where all the analysis are being run side to side, and where we make sure that operations are not deduplicated. Basically, if it's a step that's needed for many different analyses, it's just being done once. And then what we're left with software-wise is this kind of onion line structure. In the inner center, we have the AMPEL core agnostic part that's really working with scheduling specific pieces of software and shuffling data to and from the database. Around it, we have then a set of interfaces, so basically abstract Python units that add functionality that makes the software components look more and more like the standard software that, in our case, are available to or common to use for astronomers. So in the end, you have a layer where the data constructs that are provided to users look exactly like the light curves that an astronomer is used to working with. Can also say one word about how contributed units from different groups are integrated. That's a core aspect of this modular setup. Basically, anyone can construct AMPEL units by fulfilling these abstract class definitions, and then you can publish them, for example, on GitHub. Other users can clone them into their local system, and where they will be recognized as AMPEL units, or units that AMPEL can execute, again by fulfilling these abstract definitions. Okay, so I'm briefly going to talk about this third mode where AMPEL is a live scientific engine by talking about the live instance running at the DSE Soiten Computer Center. So here we're parsing data from the Zwicky Transient Facility Observatory in California. So this is every night monitoring the nighttime sky for transients. And these are being processed then for a number of different science programs in parallel. And unfortunately, I won't have time to talk about them in detail. But might be looking for these neutrino counterparts for gravitational lens supernovae, for kilonovae, thermonuclear supernova explosions, or for TD. So all of these are different science programs running in parallel and all producing exciting results. I do want to talk a little bit about these technical aspects of provenance and fair data, since it is an NFDI focus, and it was kind of a focus also of AMPEL from the beginning. So how does this manifest? One of the immediate aspects is that all the records are seen as immutable objects, meaning that new data is only added to the AMPEL databases. As similarly, the results of your computation are added. And if you're updating calibration or tweaking your algorithm or getting new data, what happens is that you create new states, and where, for example, some data might not be there anymore and some might be. And in this sense, you effectively have a time machine where you can always go back and see at some early point of time what sort of data existed and what were my conclusions at that time. Continuing this kind of technical aspect, every time you run an AMPEL system, the configuration you're running is automatically saved together with the full analysis schema and the versions of the full AMPEL system. So it means that even if the user is not thinking about it, the exact software state that was being used can be recovered. And then finally, we have this aspect that the workflows are encoded as analysis schema, and these can be used for reproduction as well. You can send it to your colleagues for them to continue working with, or you can publish them for other readers to reproduce your results, or you can execute them at a high-performance compute center at scale to, for example, read a massive live real-time data stream. We, of course, have a lot of gory details, and these are the things that we'll not talk about. It's an open source project, mainly in Python. You can find the link there. In the background, we have a NoSQL MongoDB database. And then there are many aspects that we had to work on, the two execution modes, how to help with the modular integration with software from many different users, authorization, REST API. So I think these are also aspects that are common and that we can talk about, but that I will skip for now. Instead, I'll try to summarize a little bit how this workflow design process looks for a user in astronomy. So it's this three-step process. In the first, you design your workflow. You highlight what is it that you want to do, and you break it down into tasks following these different tiers, the 4 tiers that I described above. And this brief example shows in the beginning, you might, for example, retrieve a sky map from like Virgo, and you combine that with other set of data, you filter the data, and you perform calculations. And you install the local AMPEL environment and you run your workflow there. Typically what happens is that one part, hopefully most of the components of your workflow already exist as module that you can just use. But what makes your study specific usually has some sort of additional algorithmic evaluation. So this you then add as a new AMPEL unit. And then you develop this and you test and tweak your workflow locally. And then in the third step, you run or export your data. And this could mean, if you're a software developer, it could mean that you're uploading your unit into an area where other people can use it and reference it. Or it might be that you publish your workflow for reproduction by other, or it can mean that you then upload it to a computer center to actually run it on large data sets in real time. Okay, so hopefully we're running towards the end, and I wanted to revisit these use cases that I mentioned before, maybe it makes more sense why they're all relevant to the kind of use cases and the needed we have in astrophysics. So we're certainly dealing with real-time streams from the telescopes that we need to analyze. The software development is very modular. We're looking at integrate with different science groups, each with different needs and each that have their own theory that they want to implement and combine. We have heterogeneous input sources coming from different kinds of telescopes that we need to combine in a way that's accessible to normal users. Fine-grained provenance is important since we don't know what the universe will be up to. We really want to understand what data we had at some point in time. And it's also very common that we're rerunning data, analysis of the same data. For example, it could be a machine learning classification of a transient, but then different users make different use of that data. So we can deduplicate those operations. And then again, this in general, a lot of those things means that what we've done in practice is to enable code to data in science. These are instructions for installing AMPEL locally. I think that the modules that are existing here, they all have an astrophysics focus, so might not be directly interesting, but I leave the instructions there. And then get to my summary. So astronomical transients today allow us to test fundamental physics by using the universe as a lab. To do that, we need to deal with large and heterogeneous data streams. And we designed AMPEL as a toolbook or a methodology or workflow manager to allow us to really use these data streams and to do that while being flexible, while also providing a scalable analysis engine. The core of AMPEL is domain agnostic and open source, and the tools in there can be used basically for all of the science cases that are listed before. And again, if these are problems that you've encountered, I'm very happy to discuss that further. Or if you have suggestions, that's also certainly something one can collaborate about. In the end, in the bottom, we have some more links to more information. The overview paper is very old by now. We will hold tutorials within Punch for NFDI, and of course, everyone is welcome. But really, the best way to continue this discussion is to contact me directly through the email below. Thank you.
So thank you very much for this interesting talk. So now we have to say goodbye on YouTube for our spectators there. Our next episode of the NFDI talk is on 4 November, and it's about federated data analysis with data